Hey everyone, let's take care of that last question on your vector components note. We'll do this example together. The sound quality is pretty bad, so please just bear with me as we try and go through this together. Okay, I've got velocity vectors here, 46 meters per second, north 80 degrees to the west. And then we're adding another velocity vector, 117 meters per second, south 40 degrees to the west. The first thing we want to do is make a drawing to see what this looks like. That's always going to be our first step if we don't have a diagram. All right, so let's draw our picture here. I'm going to grab this box and I'm going to put it, say right here. We're going to draw our first vector from there. Let's draw arrows. Let's make it red. Now this one says it's north 80 degrees to the west. So that means we're really close to the west. Not the whole 90 degrees, but we're like getting close. So it looks kind of like that there. And let's put in our angle. If it's north 80 degrees to the west, that means this little sliver that's left over in here, that's got to be 10 degrees. I'm going to label that one because that's the one that's adjacent to the horizontal x-axis. Okay, next let's hop over. Let's get this other one. I like drawing the little dotted line. This helps me know where to draw from and check my angles. This one says it's south 40 degrees to the west. So we'll get another vector here. We'll make this one red as well. And we're going to draw tip to tail from here, 40 degrees from the west. And this one is bigger than our other one. So I don't know that I can make it its full size and make it still fit, but I'll draw it to about as far as I can there. And that means if this one is 40 degrees from the south, because we started at south and then went 40 degrees to the west, this has got to be 50 degrees right in here. Now, our resultant vector is going to be the one that goes from the beginning to the end. So let's put our resultant vector on here. Let's make that one, let's do a nice purple color. It's going to look like that. This is a velocity vector. So I'm going to call this VT for my total velocity. I'm going to put a little vector hat on top of it. When we do our directions, we're probably going to want to use this direction right in here, this direction theta. And we don't know what that angle is yet. We're going to have to figure that out. But that will allow us to describe it from the western direction. How far south does it go? We're going to need to use our vector components to solve this problem. So let's go back to our full screen here. And let's start putting in our vector components. We're going to do our x and our y components, and then we're going to do the sum. First thing we'll do is we'll write in our vectors. We've got one that is 46 meters per second, and the direction is going to be, it's easier if we look at it from west 10 degrees to the north. We could have written it as its original direction, but north 80 degrees west, but this is going to write it in a way that makes it a little easier for us to know what angles to use when we're doing our vector components. Our other one is bigger, right? It's 117 meters per second, and our angle is west 50 degrees to the south. Okay, now if I just do a little sketching on my diagram here, I can see my first vector. I'm going to get a positive y component and then a negative x component, because it's going to go towards the left, that's towards the west, and we're calling that our negative direction. We can remind ourselves that when we do this, right, our convention is to say north, south, east, and west, and we're going to say north and east are positives, and south and west are our negatives. Okay, so let's keep filling in our chart here. We actually don't need the third one, so we can cross that out. We only have two vectors that we're adding here. Let's do our vector components. Our x component of our first vector. Okay, now I drew the components up here, but I could actually take, ooh, come on, can I split you up? No, it doesn't want to let me. That's okay. What I'll do is I'll get rid of these. And I'm just going to draw them in like this. Our x component is going to be like that, and our y component is going to be like that. That's identical to what we had before. So we say, okay, our x component here is going to be the magnitude of the total vector, that's 46. And then it's going to be the cosine, because cosine is adjacent ones, right? And that x component is adjacent to that 10-degree angle. So 46 cos 10. Let's also make sure we got our signs correct. This one is going to be a negative, so we'll put a negative sign in front of it. Let's figure out what that is. When we plug that into our calculator, we're going to end up with negative 45.30116. I'm just going to write it to 5 decimal places. We'll round off at the end of the problem. Our y component actually goes up for this vector, so it's going to be a positive value. So I'm going to say 46 sine of our theta. That's sine of 10 degrees. We use sine because our y component is our opposite side to that 10-degree angle. Okay, plug that into our calculator. We get 7.98782. So we have our x and y components for our first vector. Let's look at our second vector here and do our x and our y components. I notice my x component is going to be a -1. It's going to go like that. It's in the west direction, so it's negative. And my y component is to the south, so that's also going to be a negative. I'm going to have a negative value for both of these. So I'm going to start off just by making sure I indicate that those are going to be negative, because that's the direction those are going. Okay, let's put in our values. Our magnitude of our vector is 117. And then we're going to say cosine of 50 degrees. Again, because the x component is adjacent to the 50-degree angle, so we use cosine for that one. When we work that out, we get negative 75.20615. Our other one, we said it's a -1. It's the magnitude of our full vector, 117, times the sine of 50 degrees. We work that one out and we get negative 89.62720. Okay, so we've got our vector components. Now we're going to do the sums. We're going to add all of our x components together. We've got 2 of them in this case. We're going to add all of our y components together. We've got 2 of them in this case. So let's do that adding. Negative 45.30116, negative 75.20615. Add those together, we end up with negative 120.50731. Let's take stock of what this means. A negative x component means it's going to the west. Now, our negative x component, right? If I come out of my full screen here for a minute, let's just find our highlighter. There's our highlighter. We're looking at this one plus this one. We add those 2 together, and we get that negative 120. Now we're going to add our 2 y components together. We have one that's positive, it's going up, and one that's negative, it's going down. But the one going down, one going to the south, is bigger. So when we add those 2 together, we'll end up with an overall southern value, an overall negative value. Okay, let's add those together. 7.9872 and negative 89.62720. Add those together, we're going to end up with negative 81.63938. Okay, those are our 2 vector components. Now let's actually draw the triangle of those vector components added together. We know their values, let's draw what the triangle would look like. The triangle is going to give us the same resultant as that purple one in our first diagram, our overall velocity when we sum those 2 velocities together. Let's extend our page and let's actually do that triangle. Okay, here we go. We'll draw our triangle. Our first one, our x component is negative, so we know that means it's going this way, to the west. And it has a magnitude of 120.50731. You might have said, Mr. Roy, why didn't you put the negative on there? I certainly could, but because this is a diagram, I know the negative means west, and I'm actually drawing it to the west. So I don't actually need to indicate the negative on there. You could, it wouldn't be wrong, but it's not necessary when we're drawing a diagram. Here's our y components when we add them together. We end up with 81.63938. Okay, we've got our right angle triangle. Let's do our resultant vector. And our resultant vector is going to look like that. This is the exact same. We're going to say this is our total velocity. This is the exact same vector as the one above. You'll notice that they look the same, they have the same angle, and they have the same value. So this vector components is just a way to figure that out. Our x component is made of our two x components added together. Our y component is made of our two y components added together. Okay, there we go. Now this is a right angle triangle, right? So we can use our good old Pythagorean theorem for this. We have all of this on the flow charts. You can also follow the steps on your flow chart. Let's do the math. We're going to say the magnitude of the velocity, just to figure out the magnitude. Using Pythagorean theorem, it's going to be the square root of 120.5071 squared and 81.63938 squared. If you put those in as negative values, when you square them, they become positive, so it would work out the same. That's why I didn't worry about the negatives there. Okay, work that out. It's going to be 145.55755. Okay, that's in meters per second. Meters per second is what we've been working in this whole time. We need to get our angle, so let's keep going. Let's get our angle. Our angle theta, in this case, is going to be right here. And if we go back to the top, we'll remember that we've seen that angle before. It's right there. It's the one we labeled theta. It's the same angle. So here we go. Let's find the angle. We're going to do the tan inverse because we've got the opposite and the adjacent side. Tan is opposite over adjacent. Our opposite side is the 81.63938. And the adjacent side that's attached to next to that angle, adjacent to it, is 120.50731. Okay, we're going to work that out and see what that works out to. Let's do the math. We end up with 34, this is in degrees, 0.11623. Now we're going to round things up. I did at the beginning of this problem, my angles only have one significant digit. That's going to make us round off a lot. So I'm going to beg your forbearance here. And let's just pretend that my angles were written as if they had 2 sig figs, because I don't want to round off that much for this example. So if we round off to 2 sig figs, our velocity, the magnitude is going to round off to 150 meters per second. And now we do our angle. Now we notice that angle is to the west and then going down towards the south. So if we want to write this the easiest way, we could just write it as west, 34 degrees to the south. Now if you wanted, you could write this as south and then capture your angle going to the west. That's also correct, equally correct. And I'm very happy with either of those. You would get full marks if you put either of those around it. Final answer, so let's put a box around it. Okay, that is your second example. Now that we've got that, it's time to do some practice on this stuff. And some of the practice we're going to try actually will have 3 or maybe even 4 vectors that we're going to add together into our table. But the method remains the same.